Скажите, пожалуйста, вы видите мои слайды?
Да.
Хорошо. Ну хорошо, тогда я думаю, мы можем начинать. I switch to English because some of our listeners are not yet Russian speaking. And this is our first seminar in this new year. As usual, it is on Thursday afternoon, every week or sometimes not every week. And today I will talk about our last works about epidemic modeling. We have done these works during last, in fact, already almost 3 years after the beginning of this COVID-19 epidemic. And what I will try to do today is to introduce a new class of epidemic models and to discuss some of their properties. And this is a joint work with my colleagues from India, Mali Banerjee and Samiran Ghosh. So this is what it is about. Today I will start about the classical I'm sorry, I would like to ask everybody to switch off microphones. So first of all, I will recall this classical SIR model because I will need it further in my presentation. Then I will introduce some new models, and we will show how these new models, in some particular case, can be reduced to this SIR model or to some other models. Then we will compare these models with the data. And at the end of my talk, I will discuss one more question about vaccination and immunity waning. So, of course, everybody knows now this SIR model. It's susceptible, infected, recovered, written here, introduced about 100 years ago. It's 3 ordinary differential equations for the number of susceptible individuals, for the number of infected individuals, I, susceptible denoted by S, and for recovered R. So there are 2 main assumptions in this model. The first assumption is that the number of new infected is proportional to the product of the number of susceptible and of the number of infected. This is quite natural assumption, and if we compare with chemical kinetics, it reminds us what is called mass action law. So the number of susceptible decreases with this rate, the number of infected increases, and also another important assumption is that these infected become either recovered or dead. This is one more equation for dead is not written here. And the assumption is in fact that the number of recovered, newly recovered, is proportional to the total number of infected. So this is why there is minus gamma I here and plus gamma I here. This is an important assumption, and I will return to it later. But now let us recall some main properties of this model. First of all, the solution is shown here qualitatively. The number of susceptible, it's a blue curve here, monotonically decreasing. The number of recovered, monotonically increasing. And the number of infected first increases and then decreases to 0. There are several main characterizations of this model or of the epidemic described by this model. The first one, of course, is the basic reproduction number, written here. And the meaning of this basic reproduction number is that if we determine the number of infected at the initial moment of time, so it can be written in this form. It's an exponential, and here in the exponent there's this R0 minus 1. So if R0, the basic reproduction number, is larger than 1, the number of infected will increase, otherwise it will decrease. So this is the main property of this model, and of course it's very famous, very well known, and for example, all this last 3 years we listen the information about this basic reproduction number, whether it is larger than 1 or less than 1, and of course all that was largely discussed also in the scientific literature. Another important characterization of the epidemic described with this model is the final number of susceptible individuals. So if we take the asymptotic for large time and we take this function S of t, so it has some limit at infinity. We call this limit as f, final number of susceptible. And there is also very well known and quite simple calculation how to find this limiting value. Well, several integrations, and it's very well known. I will not stop at that. And doing these calculations, we obtain this equation written here for this x here. It's the ratio of SF to the initial number of susceptible or to the total population. So this x, so we have this equation logarithm x equals R0 x minus 1. And of course, it's a very simple analysis which shows again that if R0 larger than 1, then there is a solution of this equation x less than 1. This means this x less than 1. It means that the final number of susceptible becomes less than the initial number, and this shows that the epidemic progresses. So again, this is important here that this equation has a solution x less than 1 if the basic reproduction number is larger than 1. And the last property of this model and of the epidemic, truly speaking, I don't know whether it exists in the literature. I did this very simple derivation in some of the previous works. So I don't know whether it was known before or not, but similar to the final number of susceptible, we can also find the maximal number of infected individuals, also just some simple calculations. I will not stop on them. So why this maximal number of infected individuals can be interesting? We see this maximal number of infected because if we want to estimate, like from the point of view of public health, the number of, well, acceptance in hospitals, things like that. So we need to know this maximal number of infected, and in fact, we obtain explicit analytical expression for this value. So all that is very well known, and just to finish this short introduction about SIR model. So what we can say, it's a classical model, very well known. It is simple, it is widely used, it gives very nice and qualitatively correct results. So everything is perfect, except for that some assumptions of this model are not justified, and the result of this model are not precise. And this is exactly what I'm going to discuss in my presentation today. And we will introduce some other models, and we will compare these different models. So what is the problem with this SIR model? You remember I mentioned that there are two main assumptions, and the second main assumption is that the number of newly recovered, is proportional to the total number of infected. So if we want to know how many recovered people are today, according to this model, we take the total number of infected also today. But clearly, this is not possible because if the duration of the disease is, for example, 2 weeks, so people who recover today, they became infected 2 weeks ago. So we should not take the total number of infected today, but we should take newly infected 2 weeks ago. So this is another assumption, and this shows, and we'll analyze that, and this shows that this SIR model may not be exactly precise because this assumption, in fact, is not very accurate. This is why I will introduce now some other models. We call these models with distributed recovery and death rates. And the main idea of the derivation of this model is exactly as I just mentioned. So let us take the number of newly infected people, it is called J here, at some moment of time eta. Or if we look at this graph, the left graph in the slide, so let us take the number of newly infected people at day 0. Then we can use the data available in the literature. In particular, these data are taken for this COVID-19 disease. So if we take all people who were infected at day 0, there is some distribution shown here, which shows us how many people, or well, percentage of probability to recover certain number of days later after these people were infected. For example, for this COVID-19 disease, you see this distribution here. We take all people infected at day 0. So this distribution has a maximum at day 7. Of course, it depends on virus variant. These data were obtained for this Delta variant, but now it's not important for us. I'm trying to understand the main ideas behind this model. So we have this distribution, and we see, of course, there are very few recovered on day 1, a little bit more on day 2, then many of them at day 6, 7, 8, and then this distribution decreases. So we should take into account this probability of recovery after infection. And if we do that, then we can calculate the number of newly recovered people at time t. So then this is this integral. So J of eta, it's the number of newly infections and at day or at time eta. Then we take this time difference between t and eta. This r, it's exactly this distribution. We suppose that we know it. And like that, with this integral, we obtain this newly recovered, or in other words, dr dt, and the same for dead. So I summarize. This is, I think, quite straightforward, but it's important for us to understand that once we know or introduce the number of new infections, we can calculate the number of recoveries and the number of deaths at every moment of time. Of course, we need to know these distributions. If we do these assumptions, then we obtain the following model. So this equation for I, written here, it's these two terms are exactly as I described before. But also what we introduce here, it's the time-dependent infectivity rate. So it's also a little bit more complex than in SIR model. We know that infectivity also depend on this time after infection. This is why we have here another kernel depending on this time difference. So this is how the number of susceptible changes, the number of infected. We have the same term here, then the number of recovered and the number of dead. This is now our complete model, what we call with distributed infectivity, recovery, and death rates. But in what follows today, I will consider a simplified model. In fact, you see this term now in the first equation, instead of not as I just showed here with distributed infectivity, but we take a constant infectivity and write the same term here as in the SIR model, and also the same term here. So this is the number of susceptible changes like that, the number of infected increases like that. And what is J of T is the number of newly infected. This is exactly this expression written here. So now we have this complete model with distributed recovery and death rates. Of course, we can, well, this is a system of integral differential equations. We can discuss some mathematical properties of this system of equations. And some of these properties are studied, like, for example, existence of solutions or positiveness of solutions. I will not discuss these properties today. Positiveness is important, and it's not very difficult to prove. Existence, it's really more mathematical question, and it requires some development, so we will not stop on that today. Well, the next question, which is quite interesting from my point of view, is how this model with distributed recovery and death rates, how this model is related to this SIR model. And in fact, indeed, we can reduce this left model to the right model. And how we can do it, we need to do some assumptions on this distribution, recovery, and death distributions. And in fact, the main point here is that we assume that these distributions are in fact constant. So we introduce parameter tau, which is disease duration, and we say that during the whole disease, the probability to recover is constant. The probability to die is also a constant. And if we do these assumptions, and if these constants are sufficiently small, and this is usually the case, then under these assumptions, we reduce this distributed model to the SIR model. So what is interesting to understand here, that it's these assumptions on the distributions. We saw before that these distributions are given, well, we can more precise. So in fact, these red curves shown here, these are bimodal gamma distributions. Sometimes we can also use simple gamma distributions. This is not important here. But what is important is that these distributions are not at all constant. So this is where this difference comes from. For the SIR model, we replace this distribution by a constant distribution. Why it is not the same? Because in particular, in the beginning, very soon after the infection, there are no recoveries. But in SIR model, we assume that there are recoveries with the same rate. So this is the main difference between these distributed models and SIR models, and we'll see later that this difference in the model formulation will give also the difference in the results. Another reduction, another simplification of this model is shown here. we can reduce this model with distributed parameters to model, we call it just delay model, or it can be also called point-wise delay because such kind of models at the left sometimes also called models with distributed delay. Then here it will be with point-wise delay. So what is why we do that? Because these distributions of recovery and death, well, in some cases they are more or less known. For other cases they are not known.
Professor Wольperт, excuse me.
Yes, please.
It seems like we have one question. Can we ask
Yes,
them?
Thanks a lot. Thanks a lot. Should we put the coefficients R0 and D0 in the second equation before J of T minus tau? Why is this coefficient equal to 0?
Excuse me, what equations?
If you take a look at the SIR system to the right.
Sorry, SIR, it's a previous slide. It's this one. Yes.
No.
Okay.
I'm sorry, the generalization. Please return to the slide we were a minute ago.
Is this one?
Yeah, thank you. I don't understand the second equation of the system on the right. Because you extract J of T minus tau, and it is not equal to the sum of recovered and dead people. Why is it so?
No, in fact it is, because R0 plus D0 equals 1.
Okay, thank you.
Sorry, maybe I should, yeah, you're absolutely right. I should write it here, but I forgot about it. Yes, but now if we consider another form of these distributions as delta functions written here, then we can reduce this distributed model to this pointwise delay. And of course, this is also a simplification, but it is as useful the simplification because here we don't need to know exactly the form of these distributions. And as before, tau here is the duration of the disease. So of course it is an approximation. So you see, if we return back to this distribution, for the SIR model, we replace it by a constant distribution. And for this delay model, we replace it by a delta function concentrated here for some average disease duration. So it's completely different approximation, but of course also an approximation. And we will see how this approximation will work. So in fact, we have now these three models, this distributed model, SIR model, and then this pointwise delay model. And we compared these three models between them. And the comparison is shown here. So this blue and green line, so I even don't know, they're so close that I don't remember which of them is which, but these two lines, blue and green, these are delay model, distributed delay and pointwise delay. In fact, they give very close results. But this red line is SIR model, and it gives a different result. And in particular, if we look at this right graph for the number of infected people, this red line, so first of all, the maximal number of infected becomes less, and the time to maximum becomes larger. Why the maximal number is less? Because as we discussed just before, for this SIR model, the distribution is constant. This means that people begin to recover right after infection. In reality, this is not the case. So in SIR model, people recover in some sense faster, and this is why the total, the maximal number of infected becomes less. This is what is explained here. So I recalled very briefly in the beginning the analysis of this SIR model for the basic reproduction number and other characterizations. Similar analysis can be done for this delay model. Again, I will show it very briefly. We will not discuss the details, but we can also determine the basic reproduction number, which is shown here, and the same beta, the same S0 and N, but now we have this basic reproduction number, depends on tau. Tau is disease duration. If you want then to calculate the final number of S, we obtain exactly the same equation as for the SIR model. Here, well, it would be better to write here R0. In fact, it's R0 here. So equation is exactly the same, but the value of R0 can be different. Finally, the maximal number of infected individuals. Well, in this case, calculations become a little bit more complex, and we cannot obtain exact analytical solution in this case, but we can obtain an approximate analytical solution. I will not show the derivation at some calculations, not so important now, but the result is just shown here in this graph. So in fact, this one of these curves is the numerical solution of this full problem, and another curve is this approximately analytical solution, and these two curves are very close. So though the solution is not exact, but it gives a good approximation. Now what is interesting is to compare these three models with the epidemiological data. We have done it in recent works. I will try to explain you how we do that. And I begin with the distributed model. So we begin with this number of new daily infections, called here as before J of t. So we take this number from the epidemiological data. What I show here is as before this COVID-19 disease, and the graphs on the left, it's for different countries. So all this data are available. So we take some particular country, and from the available data, we take this J of t, the number of new daily infections. So we know that. Once we know this J of t, and also we have these kernels R of t and D of t, distributed recovery and death, we can calculate these integrals, and we can, by that, we can find this function called sigma of t here. This is daily recovery and death. So this formula gives us daily recovery and death if we know new daily infections. So let us look at the graphs now. So let us take, for example, the first row. I don't remember exactly for which country, it's different countries, but it works equally well for all of them. So in the left graph here, what it is shown, it's daily recovery and death. So it's exactly this function sigma of t. The dots, black dots, are data from its epidemiological data, so the real data. And the blue curve, it's what we obtain with this formula. Again, I repeat, we take J of t from the data, we obtain sigma of t, and we compare by this formula, and we compare sigma of t also with the data. And this comparison is shown in this graph. And we have exact correspondence between the data and this calculated formula. So we show, again, but of course, well, we should understand what we do. We take J from the data, we obtain sigma, we compare sigma with the data. So this is, of course, based on the data, but we obtain exactly the same in this formula. We obtain exactly the same as in the data. If we do,
Wольperт,
yes.
Excuse me, we have one more question, please.
Yes,
Alexei.
yes, please.
I'm sorry for
yes, please.
so many
no
questions,
problem.
but
Okay. Yes.
What data was used to evaluate the kernels? I mean,
yes. So yeah, I understand your question. Yeah, these data are available in the literature. So we took, in particular for this, formulas and this form of these kernels we used here, it was obtained, as far as I remember, we took for different countries. And truly speaking, I don't remember. I think that here it was taken for Canada, because the problem here is that, well, on one hand, the data, these kernels, the distributions are known, but you will not find them for all countries. So this is one of the limitations, and this is why then we reduce to this more simple model where we don't need the form of this kernels. So we use several of them, simple gamma distribution, probably taken for China, I don't remember now, and there's a bimodal gamma distribution taken for Canada. Both of them were taken from the literature. And of course, they were obtained from the clinical data, these distributions, for this particular disease. But then we used exactly the same kernels for other countries. This is what I'm trying. I hope this is clear. So we take, since not for all countries we can find this data, we take these kernels R and D for some countries, and then we apply them for all other countries. In particular, here there are 3 different countries corresponding to 3 different rows of these figures, and for all of them we take the same kernels R of T and D of T. So if I answered your question, then I will continue. So we see in the left column, this is comparison between daily recovery and death. This black dots and blue curves for 3 different countries. For all of them, there is a good correspondence. But if we take, if we do the same for the SIR model, this is magenta curve, and this becomes quite different, as we see here. And in the right column, these are now calculated total recovery and death as functions of time. This is now, we take this full model shown here, we solve these equations, and we find these functions R of T and D of T. And then these functions are shown here. Again, here there are black curve. It's taken from the epidemiological data. Blue curve, it's what we obtain with the model. And magenta curve is for the SIR model. As before, we have more or less exact correspondence between this distributed model and the data, and SIR model gives different results. So next we compare the results with this pointwise delay model. So I would like to recall that in this pointwise delay, we replace these distributions by the delta function, and this delta function is concentrated at time tau. Tau is disease duration. So the first question is how we can determine from the data the duration of the disease, because we needed then to do this comparison. So this is explained here in this slide. We have this equation di dt equals this difference j of t minus j of t minus tau. Suppose that at some moment of time this derivative di dt is 0. This means that we take the maximum of this I of t function. Again, we take available epidemiological data for some particular country. Here in particular, it is done for Italy, but this is not important. It's exactly the same for all countries. I mean, the method is the same. So we take this function I of t, shown here in this left graph. At some moment of time, this function has a maximum. then the derivative di dt equals 0 here. So this derivative equals 0. This moment of time we call Tm. So at the moment of time Tm, we have this equality shown here. J of Tm equals J of Tm minus tau. So now in the right graph, we have again this blue curve. These are data, epidemiological data for Italy for some period of time. This blue curve. In this blue curve, we take the moment of time T of m. It's exactly the moment of time where this I of t curve has maximum. Well, for example, it is here something like 280 days. So Tm equals 280 days, something like that. So we take this 280 days here, and we determine the moment of time such that these two values are equal to each other. So we just take the same value and we find this previous moment of time with the same value. So the difference in time, it's exactly this disease duration tau. Okay, so now from the data, we can, using the data for I of t and j of t, we can determine disease duration. And we have done it for different countries and for the same country in different periods of disease duration, of epidemic progression. And I will not stop on this analysis, though it is quite interesting to compare different countries and different times, because the disease duration, it appears that it changes. It also depends on the virus variants and so on. So we did some analysis of that, but I will not stop on that today.
So, may I have one question?
Yes, please.
Could you please recall what is I of t and j of t? I of t is newly infected.
I of t is the it's the total number of infected at the moment of time t.
Mm-hmm.
And j of t, it's the number of newly infected at the moment of time t.
Thank you.
By the way, well, once you ask this question, we can, from this point of view, analyze this equation written here. What is the meaning of this equation? So di dt, how it changes, right, at moment of time t. So we take the number of newly infected in the right. It's how di dt increases, right? But we should subtract those who become recovered or dead. And this recovered or dead, these are those who were infected tau time before. Is it clear, Anastasia? This is why we have this difference here, and it gives us exactly the change in the number, in the total number of infected. Okay, it's those who become newly infected minus those who become recovered and death, and recovered and death are expressed, well, through the number of newly infected time tau before. So it's a very simple meaning of this equation. Okay, I continue. So like that, we determine the disease duration from the data. And now, when we know this tau, we can compare with the other data, and we do as before. So we take this j of t from the data. It's the number of new infections at time t. We take it from the data. And then we can find this daily recovery and death. It's just this j of t minus tau with these coefficients r0 and d0. Why we take exactly that new recovery and death? Because this data are available. If you open the huge amount of data for COVID-19 epidemic, and this data usually shows new daily infections and new daily recovery and death. So all this data are available. So we take this J of t from the data, and we determine this this R and D, newly daily recovery and death, and the results are shown here. As before, black dots are data, and blue line, this is what we obtain, and as before we have more or less exact correspondence, and as before SIR model gives a different result. And we do the same as before now with total number of recovery and death. These are blue and black curves here, and for SIR model is this magenta curve. Okay, so in fact, this is what like the main point of my presentation. Now I will show some other results and models just more quickly. In fact, we started to develop such kind of models in the beginning of 2020, when, well, after the beginning of this epidemic, and we started with this model. It is quite similar. So we have what is written here. It's this new infections, new daily infections shown here. Just we did not use at that time this notation J of t. It was written like that, but the ideas were the same, and we use it for not for the disease duration, but for the quarantine duration. But anyway, the main ideas appeared at the time. And more recent work, we consider this distributed model with age-dependent population. Well, all that becomes a little bit more complex if we take into account how all this susceptible, infected, and recovered depend on age. Well, I will. There's something new and something interesting compared with the previous results, but I will not stop on that in detail now. And in the last part of my today's presentation, I will discuss a little bit the question of vaccination and immunity waning. So, as before, we consider this distributed model shown here at the bottom of the slide, with one difference, but quite important. The equation for S of t, before it was a differential equation, ds dt equals this minus beta si, as shown here. Now it is different. Now we take into account vaccination, and vaccination changes the number of susceptible. Moreover, not only vaccination changes the number of susceptible, but recovered, they have acquired immunity. And this acquired immunity, it also acts during some time, and then it decreases. So this is why recovered after some time become again susceptible. So we have two additional factors here. First of all, we have vaccination, and vaccinated people after some time become susceptible, and recovered people, they have also immunity during some time, and after some time they also become susceptible. How to take this into account? We call it population immunity, shown here. Let me try to explain shortly what is written here. This V is the number of vaccinated people, and okay, to make it simpler, I will not discuss all this 1, 2, 3, and so on, because we considered, in fact, different doses of vaccination, first vaccination, second vaccination, booster vaccination. This becomes complex. I will try to explain you the idea. So we take the number of vaccinated people again from the data. we don't have equation for vaccinated. We take it from the data. In other words, we know these functions V of time. It's the number of vaccinated people. Next, we know also from the data how long this immunity, vaccination-induced immunity acts, and this is described by this kernel. Also, we take this kernel from the literature, and this integral gives us this V prime, it's the rate, the vaccination rate, and phi, it's the immunity kernel. This integral gives us the immunity in the population due to vaccination. Again, let us skip all these complications with different doses of vaccination, not important now. And the last term here, it's vaccination, it's immunity due to the disease. So the recovered people have also immunity during some time. This immunity distribution described by this kernel function. So like that, we obtain this total immunity in the population given by this function M. And immunity means that these people cannot be infected. So we should subtract this number of people from the number of susceptible. So before, if we don't take into account immunity waning, all this vaccination, and in the model, then this, if this M equals 0, and then we have this S, we have this total population N, and then we have S plus I plus D equal N. But now, if we take immunity, population immunity in the population, we decrease, so then this number of susceptible is not exactly N minus I minus D, but also those who have immunity. I hope this is clear. The idea is very simple. We take the number of susceptible and we subtract the number of immune people, the number of people who cannot be infected at this moment of time. So like that, instead of the differential equation for S, we obtain this algebraic equation for S, and then we can substitute it in this equation, and we obtain a closed model. So this is the model which we use to describe epidemic progression, taking into account vaccination and immunity waning. And then I will just show some results. After that, this work was published about 1 year ago, in the beginning of 2022, and we presented this graph shown here. I will explain what is shown. So as before, black dots are new daily infections. Then, in fact, in the model, we have one unknown parameter. So you see, it's interesting that this model, we use all this data, we use epidemiological data for this V, for these kernels, and so on. But there is still one unknown parameter. This unknown parameter, this is beta. Beta, this is the intensity of infection progression in some sense in the population. So the number of newly infected is proportional to the product of S and I with some parameter beta. This beta is unknown. So what we do here, we take this, in fact, this 2 or 3 weeks in the beginning, and we use this this initial period of time to fit the data. So we take these black dots and we fit this green curve. So we have this model. We calculate calculate the number of newly infected, and like that, in this initial period of time, we determine this beta by fitting the data. Only 2 or 3 weeks here, and then we continue this curve already honestly calculating the number of newly infected cases as a function of time. We obtain it using the model. So this is the blue curve. Again, green curve, we fit the parameter, the only parameter which we don't know. We find it here. Then we continue and we see that there is a good approximation of this data, black dots, by this blue curve. Then it decreases, it comes here. And this work was published exactly, and not published, but finished, submitted at this moment of time. And then it was in probably in February 2022. And so this magenta curve, it's further prediction obtained with this model, and we did not have data at the time here because it was exactly at this moment of time. So now we can compare, and we see that, so, well, in fact, it was, this slide was done like in June, so it was like that. This blue curve is the real data. So I will not do exact comparison now, but let us look at this right graph. In fact, this is all that is done for France. Of course, it should be done for each particular country. So this large peak is Omicron in the beginning of, it's the end of 21, beginning of 22. This large peak was calculated exactly here. Large peak, it's exactly this large peak here. And then we have this, it's not exactly periodic, but probably with decreasing oscillations, with not exactly the same time between these outbreaks. But anyway, this behavior, it's not exactly the same as we predicted, but quite close. And in fact, now this prediction done in 1 year before, it was done till September 22, and we had here these 2 outbreaks, and we have here these 2 outbreaks after Omicron before September 22, and then, well, this continuation, these further outbreaks, we did not do that. So we see that this model, well, not exactly, half quantitatively, half qualitatively, it describes this behavior with these more or less periodic outbreaks, and more or less the timing of these outbreaks is more or less correct. Well, what we continue now, in particular with my graduate student Masoud, we consider this vaccination problem for the delay model and also for some other problems. So this is work in progress. We see this period, not exactly periodic, but well, these oscillations. And there are a number of further, well, continuations, but in particular what I say now, we introduce also this exposed compartment, which is not, which was not considered in these previous models. And there is a number of other questions, in particular 2 virus variants, mutations, other epidemics. So there is a number of other questions for which this approach, these models can be applied. Well, these are references which I use, several works published this last years. Conclusions. So these models are introduced here based on new daily infections. It can be either distributed or point-wise delay. These models give a good description of the epidemiological data. Also, what is quite useful is that point-wise delay model gives a good approximation for the distributed delay model, and this is useful because this model is simple. We don't need to know these distributions. And finally, SIR model gives quite a different result in comparison with the data and with these models. I stop on that. Thank you for your attention.
Thank you very much, Professor Wольperт.
Okay, so if there are questions, let's discuss. If no questions, so we will not discuss, and I think that
Maybe a small question. Will you send us the presentation after the?
Well, in fact, well, there is some noise. Yes.
Will you
So
send the presentation?
yes, I understand the question. Yes, in fact, the presentation, the slides will be put in the seminar site, so it will be available as for all other seminars. But I can also, independently of this site, I can also send the presentation to if there are people who prefer to get slides directly. Yes.
Okay, thank you.
You can leave your email in the chat and we will send you the presentation. It would be faster than it appears on the site.
Okay, just a second. I'll put my email here. Where is the chat? Yes, maybe.
Professor Wольperт, may I have one question?
Yes, please, Anastasia.
Firstly, I heard about this model in this summer and was very impressed this time. And it was very interesting to listen to it more in more details. And my question is, you do this prediction for the France, and did you do this for Russia, and do you plan to do it?
Yes, first of all, I'd like to say that indeed a part of this work, not completely, but a part of this work was presented last summer at the conference, but now it is more complete with this delay model, not only this distributed model. All right. So you see, to make these predictions, in particular these predictions, what I showed at the end for vaccination and immunity waning, well, in principle, it is possible to do the method. Okay, the method is applicable for any country. No problem with the method. So it's the question about the data. So we should find the data, in particular, the number of vaccinated people and the number of these newly infected cases or the total infections. And this is kind of a problem because not always these data are very reliable. This is why, yes, we can apply the method for any country. I cannot say whether the results will be precise because the data are not necessarily precise. But I completely agree with you. It would be interesting to try it for different countries. And I hope that Masoud, who works on this model with point-wise delay, that he will also apply this approach to some other countries.
So I have further related question to what you said. You mentioned about the reliability of the data. How we can check this for the data?
Well, it's a very difficult question. And it was a huge discussion in the literature in the beginning of this epidemic that rather often the data are not precise for many different reasons. For many different reasons, it's a very complex question because how to determine the number of new infections? So people go and make tests, right? We will not even discuss whether the tests are precise or not. They are not exactly precise. They can give an error. But let us suppose that tests give completely precise, exact result. But not all people do the tests, first of all. There are many asymptomatic cases, which in many cases, which are not identified. So this is a very complex question. Or for example, let us take the situation in China now. It's a huge disaster. Probably you follow the events. So during 3 years, the policy, it was called zero COVID, right? Very strong restrictions. Now people were unhappy about these restrictions. This zero COVID policy was stopped, like maybe 2 months ago or something like that. And there is a huge, absolutely terrible epidemic progression in China, with many millions of people infected during the several weeks. And many people died because of that. And we don't have data. So the official data announced on those websites, they give very small numbers, which don't have anything with the real situation. So it's another reason why sometimes data are not reliable, and it can be not very reliable also to use this data for predictions. But it was a bad news, but there is also a good news. And the good news is that, okay, let us take the data. We don't know whether it is reliable or not, but let us take the data on new infections. Having this data on new infections, as I showed just today, we can calculate all these other characterization of epidemic, total number of affected, number of recovered, and so on and so forth. So we can hope that even if the data is not exactly precise, but it is the same error in the data at all steps, like for example, in new daily cases and the total number of recovered. Do you understand what I mean, Anastasia? The data may be wrong, but it will be equally wrong for new daily cases and for new daily recovered, right?
I thought about should we check this?
No, but it's exactly what we do. It's exactly what we do. What I showed you. So we take this new daily cases from the data. We use all these formulas. We obtain new daily recovered, and we compare it with the data, and we have exact correspondence. You see, so this is kind of strange. Even if the data is wrong, we obtain correct result. Well, of course, it's not exactly correct, not necessarily correct, but the result which corresponds to the data. So it's the same error in the data at different stages, at different parts of this data. This is why when we do this modeling, we obtain this good correspondence, but we don't know whether the data is correct or not. And it was a really very big discussion about the correctness of the data during this, not now, not recently, but especially the first year of epidemic. It was largely discussed. Well, and it's really a very difficult question. And also the question is whether we need to take into account asymptotic or not, how we can take into account asymptotic, asymptomatic cases or not. From my point of view, we should not too much care about asymptomatic cases, because usually asymptomatic cases correspond to low viral load. So you understand, we discuss this in other works. If you take infected individual, there is viral load in the upper respiratory tract. This viral load determines the infectivity of this individual. On the other hand, in the asymptomatic cases, this viral load is low, because symptomatic and asymptomatic cases, they differ by the viral load. Asymptomatic cases, low viral load. Low viral load, low infectivity. So in some approximation, we can say that asymptomatic cases, they have low infectivity, and in the first approximation, we can neglect them in all this comparison with the data. And so on. There are, of course, also other questions, not only asymptomatic cases.
Okay, thank you. I have no questions.
Okay, then, thank you. Okay, please, there is another question I see in the audience. Please go ahead.
How many waves of infection will be predicted in some models?
Sorry, I'm not sure to understand. Could you repeat again your question, please?
How many waves and number of waves?
Waves. You mean this epidemic waves, right?
Yeah, yes.
Well, it will be an infinite number. I did not discuss some mathematical properties of these models, but one of these properties is that, for example, if we take into account that the immunity, so acquired immunity, so recovered people, they have immunity, but this immunity is finished after some time, and then recovered become again susceptible. If we consider this such model, such approximation, such assumption in the model, then we can find stationary point, this endemic stationary point, the stationary point to which it will converge, the solution will converge for large time. And it can be shown that the stationary point is stable. So these epidemic waves will decrease in time and will converge to the stationary point with these decaying oscillations. But the number of these decaying oscillations, if we take infinite time, the number of these oscillations will be also infinite. Of course, what I tell you now, we don't take into account here new variants, right? We understand that. If we fix virus variant, then the epidemic will converge to the stable stationary point in the oscillating manner, and these oscillations will decrease in time, but the number of these oscillations will be infinite.
Yes, hi. Yes, I know some cases from cholera pandemic, cholera epidemics, and it is really big problem for humanity.
Well, of course, yes. All these different epidemics of different diseases, of course, this is very, very important. And I think that mathematical modeling, of course, it was very interesting when this COVID-19 epidemic started 3 years ago. It was amazing this how many works appeared on mathematical modeling of this epidemic, and also it was very impressive that people very far from mathematical modeling were very much interested by modeling, and they had a hope that mathematics can explain everything, and even in some sense can stop epidemic. It was completely irrational, but I discussed with many people, and it was kind of idea that mathematics or mathematical modeling is so powerful that it can explain everything and it can help us in all these epidemic problems. Of course not. Mathematical modeling cannot, of course, stop epidemic, unfortunately. But sometimes it can help us to understand what happens. Well, thank you very much for this interesting discussion. If there are no other questions, then we stop our seminar today, and I invite all of you to come to our seminars, and you will receive announcements well later. I don't remember whether we have a seminar next week or in 2 weeks, but you will receive the announcement of that. Thanks again and have a good day.
Thanks a lot.
Thank you very much. Goodbye.
Thank you very much.
you.
Bye.
Bye.
Thank you very much.
Thank you.